In this video, we will see, starting from the root of a binary tree, how can we traverse the tree, which means how can we start from the root and visit every node in the tree. It turns out that there are different ways of doing this, and we will see three different ways or three traversal algorithms in this video. Now, before getting into the details, let me remind you about traversing linked lists. And based on that, we can motivate why we care about tree traversals as well. So if you have a singly linked list, right, singly linked list has a head pointer, points to the first node, and then that node points to the second node, has a pointer that points to the third node, and so on. Okay. Now, 2, 1, 5, and 4. Now, you start from the head, and then head is a pointer to the first node, so you find out where the first node is. You process that node, whatever process means in your application. It could be that you are searching for something, right? You want to know whether or not a specific number occurs in your data structure. Or a process could be that you have a linked list that contains integers, and you want to triple all them, so all of these integers. So you want to triple the 2 and the 1 and the 5 and so on. So whatever, it could be that you just want to report them. You just want to write on the screen all the keys or all the values that you store in each and every one of the nodes. So you just want to do a cout for this data and so on, right? So it can be different from one function to another, but the commonality between all of them is that you want to go from the first node to the second node to the third node and process the information that is stored at each node, right? So you process the data in the current node and then use the next pointer to go to the next node, and then process this, either cout or double it or triple it or whatever, and then use the pointer to go to the next node. So this is called traversing the linked list. Now, for a linked list, it's pretty straightforward how you can traverse it. You start from the head and then use the next pointer to go to the next pointer to go next. And then when your next pointer is null, you know that you must stop, and that's it. You have seen all the nodes of a linked list. If it's a doubly linked list, alternatively, you can start from the tail, go to the previous node, previous node, previous node until you reach the beginning. But because of the linearity of the structure, it's very straightforward. But in a tree, it's not as clear how we can do that, because at every node we have two possibilities potentially, right? At most two possibilities. We can either go left or to the left child or go to the right child, right? So in general, we can say to traverse a binary tree, we must, starting from the root, right? Starting from the root, we must do three things. The first thing that we must do is we need to process the current node. Again, whatever processing is, if you're searching, then you compare the value that you're looking for with the value that is stored at the current node. If you're doubling the value, you double the value in the current node. If you're printing them, you print the value in the current node, whatever that is, right? To process that, that's one thing that you need to do. Then you need to traverse the left subtree, because if this is your node, then remember that there could be potentially a bunch of nodes on the left side, right? The left subtree, right? So after processing the value here, then I have to traverse the left subtree of the current node. So that's another thing that I need to do. Because remember, I want to visit each and every one of the nodes in my tree. And similarly, there might be a whole bunch of nodes on the right side, right? Which is called, if you remember from the previous video, the right subtree of the current node. So I have to traverse that subtree as well. So I need to traverse the right subtree. So these are the things that we need to do. Now, I didn't say in this order, right? So depending on in which order you do these, you can get different traversal algorithms. And we are going to see three of them. And the difference between the three is only going to be the difference between the order in which we do these three things, right? So that's one thing to remember. So we process the value or the current node. We need to process the left subtree. We need to process the right subtree. And depending on the order, we get different outputs. That's one thing. The other thing is I started with, an algorithm that is traversing the entire tree. But then in the description, I said traverse the left subtree or traverse the right subtree. So you see that by nature, when we think about implementing this, which is in later videos, um, it comes very naturally that we can use recursion. We can make recursive calls to the left and right subtrees to do the same for this binary tree here and this binary tree over here. Okay, now let's go through the first possibility, which is exactly in this order. Okay, so um, as I said, we have three options. Now, so for simplicity, now for processing, I'm going to say shout out. Just write the key on the console. So shout out, then go left, then go right. So that's option one. Okay, now let's do an example. This is my binary tree. I have 10 here, 2 on the left, not in any specific order. 7 here, 8 here, 12, 5, and then on the right, I have 9, and to the right of that, I have 13. Okay, let's see how this order, starting from the root, you process the current node, then you traverse the left subtree, and when you're completely done with the left subtree, you go to the right subtree. So let's see how that works for this example. So we start from here, 10, right? We shout out the data or the key, 10. Then we go to the left subtree. Remember, I didn't say just the left child, the left subtree. So traverse this entire thing, which means I have to visit all these 4 nodes or 5 nodes before going to the right subtree. Okay, so starting over from this, that's a recursive call. Again, we already start from the top node. So what do we do first? We print out the value at the root, and then we traverse the left subtree. So that's another recursive call. Now, I'm going to run out of colors here, but the left subtree of 2 is this entire thing. Okay, again, starting over, that's my recursive call, right? Again, starting from the top node, what do? We write the value on the top, and then what? Then we go to the left. After shout out, we go to the left subtree. The left subtree is this guy. Again, starting from the top node, what do we do first? We shout out the value, 5. And then what do? We visit the left child, or left subtree, I should say. Now, this is a leaf node, which means that there is no left subtree. So this recursive call to the left subtree returns immediately. That's your base case. If the tree is empty, traversing an empty linked list, traversing an empty binary tree is the base case. You just don't do anything. You just return, right? So it returns immediately. Then after traversing the left subtree of 5, I have to traverse the right subtree of 5. But 5 doesn't have a right subtree. So this recursive call, immediately returns. Now, think about it. How did we get to this 5? We were at 7, And we said, okay, shout out 7, the root. Then go to the left subtree. We did that. Now we are completely done with the left subtree. So what do we do after we are completely done with the left subtree? We make a recursive call to the right subtree. So now we go here. So now the top node is 12. What I do is first I shout out 12, then after shouting out the root value, I try to go to the left subtree and make a recursive call. There is no left subtree, it's empty. So the recursive call returns immediately. Then after that, I go to the right subtree, it's empty, I return immediately. And now it gets interesting because how do we get to this 5 and 12? We were at 7. We said, okay, process 7. We did that. Then go to his left subtree. We did that, and we are done. Then go to his right subtree. That's the second recursive call. We are done with that too. So we are completely done with this subtree. Okay? But how did we get to this subtree? We processed 2. And then we said, okay, after processing 2, then it's time for its left subtree. Now we've finished the left subtree of 2. Now, can you guess whose turn it is now? The right subtree of 2. So we go to the 8. And we print 8. Then we go to its left subtree, it's empty, so we return immediately. Go to right subtree, we return and immediately it's empty. Now we are completely done with this tree here, which was the left subtree of 10, right? So we process 10, we processed its left subtree. Now it's time to go to the right subtree of 10, which is this guy. So we start from the 9. We process 9 first. Current node always comes first in this option, in option 1. Then we go to its left subtree and make a recursive call, but the left subtree is empty, so that recursive call returns immediately. Then we go to its right subtree. So we go here, we can change color. Go here, and we start from 13. So we print 13. Then after printing 13, I have to make a recursive call to the left subtree of 13, which doesn't exist. Then a recursive call to the right subtree of 13, which doesn't exist. So this binary tree is completely done now. So we process 10. We process the left subtree of 10. And we process the right subtree of 10. So we are completely done. So that is called the preorder traversal, because the shout out comes before the two recursive calls, hence the name preorder. Okay? So one more time. Current node 10, go to the left. Current node 2, go to the left. Current node 7, go to the left. So 10 to 7, right? Current node 5, right 5, or double 5, or whatever you're trying to do. Then go left, there is no left. Then go right, there is no right. Backtrack to 7. Now go right. After finishing the left, you go right. Print the current node 12, then try to go right, left, there is no left, try to go right, there is no right. Now we are done with this. We did 2, we did the left subtree, go here, 8. Now we are completely done with the left subtree, go to right subtree, print 9, try to go left, there is no left, go right. Process the current node, go left, go right, there is no left and right, and we are done. Okay. So this is called the preorder traversal of this binary. That's option 1. Now we can guess, how it goes with the other two. So we can go faster. So option 2 is when the shout out is between the two recursive calls. Option 2, I can say traverse the left subtree first, then shout out or process the current node, then traverse the right subtree. Okay, and let's do the same tree. 10, 2, 9, 7, 8, 5, and 12. And finally, here we have 13. Okay. And by the way, since the shout out is in the middle, this is called Inorder traversal. Okay. So remember left first, then the middle, then the current node, then the right node. So starting from the root. We don't write 10 yet because they have to process left subtree before uh, processing the current node. So we go to the left subtree. We go to here. Again, we don't print 2 because we first have to process its left subtree. So we go left again. We don't print 7 because before printing 7, before shouting out anything, I have to finish the left subtree. So I go left again to this subtree, right? Now I'm here at this node 5. And first I try to go to left subtree, but there is no left subtree because it's empty, or in other words, that's my base case. So it returns without doing anything. After finishing the left subtree of 5, then it's time to shout out 5. And then process the right subtree of 5, but there is no right subtree, so it returns immediately. Okay, so now we are completely done with this subtree that I circled with red. Remember, that was the left subtree of 7. After we finish the left subtree, it's time to shout out 7 itself. And after that, after shouting out 7, I go to its right subtree. And same story as 12, as 5, right? We try to go left, there is no left. Then we shout out 12. Then we try to go right, there is no right. So we are completely done now with the subtree that is circled with orange. That was the left subtree of 2. So it's now time for 2 to be processed. After that, we go to the right subtree of 2, 8. We try to go left, there is no left. Then we process the current node. Then we try to go right, there is no right. So that's it. And now we are completely done with the left subtree of the root. There's no 10. The left subtree is completely traversed or processed. Now, after left, it's time for the root node itself. So we process 10, or we shout out 10. Then we go to its right subtree. Okay, so we are here now. Before processing the current node, I try to go to the left subtree, but there is no left subtree, so the recursive call immediately returns. Then the current node, which is 9. Then we go to its right subtree. And the right subtree is this single node 13. First, I try to go left because that's always the case. You start with the left subtree, but it doesn't have any left subtrees. So 13 itself, and then we go to right, but there is no right, so we are done. So this is called the in-order traversal of this binary tree. So don't process 10, go left. Go left, go left. There is no left, process 5. Then go right, there is no right. Backtrack to 7. After you're done with 5, it's time for 7. Then go right. Try to go left at 12, there is no left, so process 12. Try to go right, there is no right. Backtrack to 2. Shout out 2, then go right. From 8, try to go left, there is no left, shout out 8, try to go right, there is no right. So we are done here, backtrack to 10, and so on and so on. So, in-order traverse. And finally, the third option, the final option that we are going to talk about today, option 3, goes as follows. Option 3 is where we process the left, then right, and at the end, we shout out the current node or process the current node. Okay, and this is, probably you can guess, it's called post-order traverse. Okay, going with the same example for post-order. Nine, 7, 8, 5, and 12, and 13. So this time we are supposed to process the left subtree, the right subtree, and only when you're completely done with the left and right subtrees, then you process the current node. So starting from 10, I don't shout out or process 10 yet, because first I need to finish my traversal of its left subtree and its right subtree. So starting from the left, we go here, go to 2. Should we shout out 2? No, we have to go left again. Let me change color. I don't know how helpful changing color is, but hopefully it's a little bit helpful. It takes a little bit of time to get used to this idea of tree traversal, but when it clicks, then it's very easy. right? So you go left again, go to this subtree. Do I process 7? No, I have to go left again. So make another recursive call to the left subtree. Use purple. So we go here, make a recursive call on this subtree. Now we try to go left, there is no left. We try to go right, there is no right. So after we are done with left and right subtrees, then it's time to shout out 5 itself. Now that we are completely done from 5 with 5, we backtrack to 7, which was the parent, right? Is it time to shout out 7? No. Remember, Postorder says you're done with left, then it's time for processing the right subtree. So I don't shout out 7 yet. I go to the right subtree. 12. First go left, there is no left, then go right, there is no right. Now you can shout out 12 itself. Now backtrack, and it's 7's turn now because we are done with this left subtree, we are done with this right subtree, so now we can shout out 7. Okay, now we are done with this subtree that is circled with red. We can backtrack to 2, but we are not allowed to shout out 2 yet because we are done with this left subtree, but not with this right subtree. So I have to go right here and finish this first. So we are here now. 8, I try to go left, there is no left. I try to go right, there is no right. So these recursive calls return immediately. Now it's time to shout out 8 itself. And now we backtrack to 2. And now if you think about it, we have finished traversing the left subtree of 2 and also the right subtree of 2. So left and right are done. So now we can shout out 2. So now we are completely done with the subtree that is circled with blue. So we backtrack to its parent, which is 10, but we don't shout out 10 yet because left, then right. So I finished the left subtree of 10. Now it's time to go to its right subtree. This guy, starting from here. Do I shout out 9? No. First, I have to go to left. There is no left. Then I have to go to right subtree. So we go to its right subtree here with 13. Left, right, shout out again. Left returns immediately, right returns immediately. Then shout out 13. And now this one is a little bit tricky. Think about it. If you think about it, we were here. We finished the left subtree because it didn't exist, right? We called our algorithm, our function on the left subtree, but because the left subtree of 9 was empty, the call returned immediately. Then we called the same algorithm on the right subtree, and we are done processing that as well. So now I can process or shout out 9 itself. And finally, if you think about it, you started from 10, right? Then we said, okay, it's not 10's turn yet. We have to process its left subtree, which we did from here to here. Then we said after left, it's time to process the right subtree of 10. This guy here, that's 13 and 9. And now, when we are done with left hand subtrees of 10, we can process 10 itself. And again, here, for simplicity, I said process means just print the value on the screen. It could be anything. It could be that you want to compare these keys to a specific key that you're looking for. It could be that you want to change them in a specific way or many other things, right? So preorder, inorder, postorder, 3 traversal algorithms. All of them are based on this observation that we need to process the current node. We also need to traverse the left and the right subtrees. And depending on the order in which you do these 3 tasks, you get 3 different algorithms. Again, preorder, postorder, and it. Now, later on in later videos, we will see implementations of these algorithms in C++ as well.